the Tech Forum activity. We started the Tech Forum activity sometime in 3 years back in June. So we have completed 3 years this month, and we have around 150 members who are like-minded technocrats. We support each other. So far, we have conducted 3 symposiums on electric vehicle, several in different colleges, and Sunday tech talks are very regular. Minimum 2 tech talks online per month. Sometimes we have 3, and all our offline tech talks are conducted in Institution of Engineers Pune as well as Pune Management Association. Friends, today's tech talk is on embedded systems, and it is going to be delivered by my friend Mr. Jai Krishna Puranik, who is an electronic engineer from Nasik. He has a very rich experience. He started in 1970 his career, and he is still working. He started his career with magnetic tapes manufacturing in India. That was the only company in India who were manufacturing magnetic tapes for All India Radio, Radio Ceylon, and so many clients across India. Then he has worked with several organizations which I have listed in his biodata. Right now also he is working with a reputed firm in Nasik as a VP R&D and developing so many applications, rather industrial as well as commercial applications. His passion is for embedded systems, microcontrollers, and whatnot. Embedded system is a part of our life. Whatever gadgets we are using at home, like washing machine, refrigerator, in automobiles, electric vehicles, or your gasoline vehicles, everybody have a heart which is with embedded systems. And this is going to play a very vital role in our today's life as well as future life. Embedded system have become part of our day-to-day activities. And let us try to understand this complex technology, embedded systems. Why embedded systems? What is the current scenario? When it has started? What is the future? Let us hear from the stalwart Jai Krishna Puranik from Nasik. Without spending much time, I will request Jai Krishna Puranik to start his presentation. Thank you. Over to Jai Krishna.
Thank you, Mr. Vilas Rabde. It is an honor to me to be with you all, experts in the field. And whatever I have learned in these last 50 years, this presentation is the consolidated efforts of that. At every organization, I could learn new things, I could do new things. And this is what this presentation is going to be, because the subject of embedded systems is at the bottom of my heart, or I would say not only just at the bottom of my heart, but it is my heart. Now, we all know about, one minute, this slide, just a minute, let me. Yeah, to begin with, I would like to thank the organizers, Institution of Engineers, Pune Local Center, Tech Forum, and of course, the officials of these institutions. For embedded system, typically we see something at the center, which is a microcontroller and the circuits around that. This is a typical idea for everyone, what is an embedded controller. And we have plenty of examples in our real life. This particular slide is an old one, but it says everything in a nutshell. You will not be surprised that the designer gets some specifications or some inputs from the sales marketing team. Sales marketing gets some information from the customer. And if many of the things are not documented right from the beginning, the misunderstanding takes place. You may say that this slide is a bit exaggerated, but if you look back and check, you'll find that this kind of mismatch between what is needed by the customer and what the designer designs, it is still there. So my efforts are to eliminate such kind of possibilities and deliver to the customer what he really intended, which we will see in the subsequent transparencies. Quite often for the newcomer, it's a puzzle that where do I start? I'm interested in doing embedded systems, but I don't know where to start. So fortunately, you'll find that the embedded system covers a very wide spectrum. In Pune, you have a big ecosystem for automotive vehicles. And all over, if you say Bangalore and Hyderabad on the telecom side, Calcutta on the entertainment side. So there are plenty of opportunities, and these opportunities are calling the embedded system designers to come forward and solve problems. In my introduction, I said that in the embedded system, if the hardware is the body of the product, the firmware is the Atma of the product. And for a successful product, this body and Atma has to coexist properly, faithfully, joyfully, then you have an innovative product. So there are some examples here. You'll see that everywhere there is a usage of microcontroller that provides that innovative strength to the product. And we call that system as an intelligent system, another name for embedded system. In Pune itself, there are a number of manufacturers manufacturing washing machines. So you'll find that a lot of thinking goes into designing a washing machine. If you remember olden days, Videocon had a machine where you put clothes in one tub, keeps on rotating, then remove from that tub and put it into another tub for spin dry, this one. But nowadays that is obsolete, and you find machines which shows overload if you put excessive clothes for this one. You have a selection of water temperature. You have a selection of whether you are doing soft cloths, baby cloths. You have a child lock so that accidentally it doesn't operate. Interesting thing in the washing machine, you'll find that when you switch on, initially the drum rotates forward, backward. People wonder why it is happening, but very few people are aware that the internal BLDC motor is doing the load balancing. So they have an elaborate algorithm by means of which the clothes are rotated in such a manner that when it starts actual operation, the load is balanced. So this is something one has to know the finer details and take advantage. There are also papers available, comparison between front loading, top loading. Many people are not aware that the washing liquid or washing powders are different for front loading and top loading. So one has to go into details and understand the intricacies. So in this case, just people were fond of calling UP as UP or microcontroller as UC, and you'll find that lots and lots of information is available. But then reading that information and putting it into practice is an art which you learn by practice and by actual hands-on operation. So my aim of this presentation is to ask our participants to follow a methodical approach to the embedded system design so that they can develop product within a reasonable time frame, and they can deliver it quickly to the user, the product which they themselves have confidence of fairly reasonably bug-free and working. Otherwise, you will find that if I had started directly, what is microcontroller, how to design a microcontroller circuit, that will not do justice to my objective of requesting people to follow a methodical approach if they are not following. If they are following, then it is well and good. So here you'll find that what is that embedded system? You have a microcontroller or microprocessor at the heart of your product, and there is a peripheral circuit. One good thing that has happened from transition from microprocessor to microcontroller, actually, really speaking, embedded system started with the introduction of microprocessors in 70s. And as the silicon manufacturer realized that instead of having too many components on the board, as much as integration you can do in a purely digital microcontroller domain with the introduction of analog sections like A to D converters, sample and hold, D to A converters, comparators, it became a hybrid but monolithic chip. So here you will find that You may have one microcontroller, more than one microcontroller. You may have a very powerful graphic user interface. Many people who are small scale industry, they are happy using 16 character 2-line LCD display. At the most, now some people have started using TFT color graphic display. So you find that there are a lot of opportunities, and it requires a good study first to configure a circuit to decide what kind of memory chips we are going to use, whether the memory available within the microcontroller is sufficient or you need external memory. Sometimes if you are doing data logging, then you need definitely additional memory, because the microcontroller memory, flash memory is to hold the program, and the RAM memory is to use as a scratch pad. Some part of the flash can be used as a non-volatile, electrically erasable, electrically programmable PROM. So all those things are important, and one has to understand these hardware specific things. This is a bit old diagram where the CPU and memory is shown separate, but with microcontroller, and the most popular architecture nowadays is ARM Cortex. The M3 architecture introduced in year 2004 is still going strong. The toys and other things people use M0, but M3 is most popular. With M4, you have a very powerful mathematical processing facility. So in an embedded system, we have inputs coming from the sensor, we have output going to the actuators, and the overall thing is organized in terms of a hardware design on a PCB, where you find that these various interactions, what is shown, which is typical diagram, it is implemented. Now, why it is important, embedded system? You find that virtually each and everything is now becoming embedded, whether it is your smartwatch, whether your mobile, which recognize the faces, allow you to do everything autofocus. So everybody with the smart Android mobile has become an excellent photographer. It doesn't have to have any special skills, and you have facilities like wide angle. So there are not only just billions, but billions and billions of devices worldwide, which are using this embedded system technology and allowing everyone to do some special ideas and put it into practice in the form of a finished product. So here you'll find that, yes, we cannot think of a life today without having an embedded system around us in some or the other form. Now, you are all aware that this is a vast subject. In this 45 minutes presentation, we'll be literally touching the tip of the iceberg. Fortunately, with Google and search engines, you have voluminous information available on the internet. But again, the problem remains that where do you start and how do you use that information to your advantage? So this presentation is basically to cover basics and some practical experiences which you'll find at the end of the presentation. So understand basic concepts, know the design approach, understand what are the hardware components that you are going to need, and the equally important part is the firmware which puts together. Earlier, during the microprocessor time, people used to joke that a hardware person will blame the software person will blame the hardware person, and both will join together hands to blame the customer, saying that the customer doesn't know how to use his product. Actually, the situations are much better now, so there is no blame game. And if the teams are working in close cooperation, such a situation will not happen, and the customer will be always happy, because he doesn't look at individuals as hardware designer or software designer, but he looks as a solution provider company. So here some of the hardware aspects, like no controller today is possible with purely digital, because the real life signals are still in the analog domain. You may have front end analog to digital converters and directly I2C bus ICs that reduces your load on the microcontroller, or special ICs which provides you all the information in SPI bus compatible registers, and one has to simply read and then utilize that information. So embedded system design has to give equal importance to the analog domain and the digital domain, and one has to select the hardware according to the specific requirements. You will find that IOs typically in the form of PLCs, they have standardized IOs like relay contact outputs or transistor outputs. In case of relay contact outputs, you don't have to worry about in which direction the current is flowing through the relay contact. But in case of transistor outputs, if it is not MOSFETs or if it is general current sinking, current sourcing transistor outputs, then one has to make sure that the further system you connect are compatible to the hardware specification of your input outputs. Typically, in a bigger system configuration, you'll find that to avoid any possibility of ground loops, the inputs are optically isolated as far as digital are concerned. Providing a galvanic isolation for analog signals is little costly. So one of the good idea for that is to do analog to pulse width modulation conversion, so that the digital pulses can be comfortably and at low cost isolated, and the microcontrollers are capable of measuring the pulse width for the low part or high part, and one can calibrate the analog signal corresponding to the pulse width. Most of the products you'll find that have serial communication in one form or the other. The most popular still continues to be RS-232, and that communication port helps in your calibrating the product, in debugging the product, in terms of say providing data logging, in terms of connecting more than one devices. Of course, RS-232 is point to point, but the other version, RS-485 Modbus implementation, allows you one master and multiple slaves up to 255 units to communicate. So there are situations where you have a master controller as a PLC or PC, and number of such Modbus nodes or modules communicating on simply two lines, D plus D minus, and you have the data at a central monitoring place, electrical supervisor's room or something. You have parallel port devices. Parallel port allows you to do faster communication as compared to serial communication. Serial communication speeds have also increased. So one has to think. In terms of microcontroller, you'll find the LCDs are still, majority LCDs are available, LCD displays in the parallel 8-bit mode, but they can be operated in the 4-bit mode also. You have wireless devices. Many of the products have inbuilt Bluetooth connectivity. You may have a 2G or 4G GSM GPRS modem inbuilt into your system, and one has to know what is the field requirement, so that whether to incorporate the wireless device into your product or it can be an accessory, it can be decided. You will find that olden days when the microcontrollers were not there and microprocessors were there, they didn't have any inbuilt timers. But these timers and counting devices, whether part of microcontroller or part of microprocessor, allows you to do two things simultaneously. That is, while the microprocessor is executing the program, the timer counting devices, independent of microprocessor intervention, do the timekeeping job, counting job, and you get a performance which is close to real-time operations. Many of the things you find that if the program is not written carefully, and if the program gets into a infinite loop where it is not intended to be, then there has to be some method to force the controller to come out of such unexpected or unintended infinite loop, and that is the job performed by the watchdog timer. Nowadays, these watchdog timer, multiple timers are built into microcontroller, and they provide the facility to reset the processor and start again. But one thing has to be carefully noted, that if the watchdog timer is enabled and it is going to reset the processor, you have to have very carefully designed input outputs, particularly outputs, so that during reset time, you don't want any accidental activation of the output. Suppose you have a security system and the gate accidentally opening is not permissible. So the designer has to be taking care about the reset condition, the output states for that, and so on. Nowadays, you find that people want the performance monitoring for the product they design. So obviously, you have a real-time clock built into the product. Microcontrollers now have got 32-bit registers, which you can use as a real-time clock. And those 32 bits can be converted into the date, time, everything. People used to use the dedicated functional ICs for real-time clock. Now, one good thing is that the clock needs to continue even when the unit is powered down. So traditionally, people have been using CR2032 kind of a lithium coin cell. Earlier days, people used to use rechargeable Nikon batteries, but they had the problem of memory effect and leakages. So that has gone. People typically use this lithium coin battery, but then at the end of the life, like say after 2 years, the battery needs to be replaced. Now you have designed your product and you have put tamper-proof stickers on that. So you don't want to allow the customer to open your product just for replacing the battery. So your product has to be designed right from the beginning, where you provide an external slot, and without opening your product, the customer himself can replace the battery. In that case, you need to provide the warning on your display when the battery voltage goes down. So you have to have the battery voltage monitoring circuit for that. Though the consumption is very small, typically in nanoamps, but the battery voltage needs to be displayed and user needs to be warned early that the real-time clock may get stopped or go haywire if the battery voltage falls below certain values. I have been successfully using super capacitors to do real-time clock backup for up to 20 days, 30 days, because in certain products which is expected to be connected to the main supply all the time, you don't expect the power to go down for more than 24 hours or 48 hours. So super capacitors typically of 15 farad value are good enough to provide you 30 days backup to the microcontrollers embedded real-time clock. So, so many interesting things are there, and one has to take care of that. In terms of software, the firmware design approaches are very important. What kind of languages you use today, nowadays it is embedded C. Embedded C is a bit different than the conventional C people use, because in conventional C, you don't need any bit manipulation and interrupt servicing facility. But in an embedded C, you have all such facilities which are the requirement of the embedded hardware design. So you must know what is to be configured as an interrupt source for your microcontroller. Typically, end of conversion of a analog to digital converter will signal the microcontroller that the previously triggered conversion is over, and the microcontroller has to read the converted value. Further to that, even if you don't want microcontroller intervention for that, the direct memory access channels are provided in the microcontroller, so that the result of the A to D conversion can be directly put into the memory buffer in a transparent manner without the microcontroller intervention. Similarly, if you have serial channels, UART ports, and you have a buffer dedicated for sending the data out, the data can be transferred by direct memory access method from your memory buffer to the serial channels. Now, in this case, depending on what devices are connected on the product, like suppose, for example, Bluetooth or an IoT device, then that device requires a specific programming, which we call it as a device drivers. And that is part of the firmware design approach. If you are using, say, 4G modem, and for modem, you have standard 80 plus command set. So when you power up, you have to detect whether the SIM card is there or not, and it is valid, and identify the network service provider and proceed further. This subject of compiler versus cross compiler, earlier days, whatever the microcontroller you are using or microprocessor you are using, you could assemble the program in assembly language on the same processor. But now that has gone. You have IBM PC or desktop PC as your integrated development tool, and your C compiler or embedded C compiler, typically from Kyle, runs onto your PC platform, and the compiler generates the code in assembly language. The assembler converts that into the machine code, and that gets loaded into the flash memory of the microcontroller. So these kind of concepts are important for the embedded hardware designer to know and implement successfully in his product. Intentionally here, this particular few slides from here onward, you will find that you can simply copy this and put it into Excel file, so that these will be the rows in your Excel file, and columns will be week of the year, so that you can do planning for your project. And intentionally have put design engineers, because if you are giving a project to one engineer, you have a dependency on him. It is better that you form a team of at least, say, 3 engineers, so that they cooperate, they learn to cooperate with each other, and they contribute. So you name the design engineer, put the starting date, put the target date for completion, and first find out that what are the applicable specifications from the customer. because there is no point in designing and using our facilities as a hobby center. Ultimately, whatever the efforts we do has to have commercial benefit to the organization, whether you are the owner of the company or you are the employee of the company or you are the consultant of the company. It is your duty to satisfy somebody's actual requirements, and that starts with customer specifications. The more clear the specifications are, the better it makes for you to design the hardware. Now, some of the customers in India may not bother about any applicable standards, but the customers in Europe and China and abroad, they do bother about which local or international standards your product complies. And knowing those standards beforehand makes it easy. Sometimes the product which you are designing may not have an elaborate specification, but you may have specification which caters to the part of the product requirements. Like in an embedded system, you always have the measurement of analog parameters, analog sensors. And even if no specification exists for the product which you are designing, but you will find the specification exists for the measurement part, whether it is an electrical measurement, physical parameter measurement, one has to, even if applicable partially, one has to know these standards. Indian Standard Institution is a member of International Electrotechnical Committee in our field, or ISO organization, and you will find the cross references on the Bureau of Indian Standards website in Pune. They have office, that which are the standards which are directly following the international standards, ISO or IC, and which are the standards where they have made variation to the country specific. Australia does it, many other countries, Canada, they do it. They majoritarily 90% they follow international standards, and 10% they do some deviations specific to the country. So one thing you will realize that in one sitting, you cannot write down all the specifications. So I always insist that you must do it in minimum three stages. Define the preliminary design specs, circulate that to the intended users, get their feedback, and based on that preliminary design specification, go to the next step of intermediate design specification. In NELCO, we used to call it as PFD, IFD, and FFD, the final functional description or design specification. So when you reach a stage where now you have fairly good finalized specifications, then proceed ahead of the actual job. Don't leave it with only preliminary specification and start your work, because this is the most common delay factor which delays the product development. That specifications without freezing, they are kept changing, and the designer also gets worried and spend more time to cater to the changing specification. So always sit together, come to the level of fairly reasonably finalized design specification, and then proceed. Of course, the approval for this finalized specs from the end user or the customer is equally important. Now, how do we proceed? Many people directly start making circuit diagram. That's not a good practice, because even if you have studied, say, PIC microcontroller or Silicon Lab or ST microcontroller, it's a good idea to design first functional block diagram, because that concentrates more on the functional aspect and leave the details at the later stage, that whether you are going to use 8-bit microcontroller, 16-bit microcontroller, 32-bit microcontroller, whether your product requires a very low power design. So functional diagram will tell you at the functional aspect of your product, and as best as you can do at the functional level, you can do that. Now, any product that you design needs to have a housing. The product has to fit into certain customer requirements. So right in the beginning, you do mechanical design, not that the PCB is designed and then you start searching for the suitable enclosure for your product. So after that, you convert that functional block diagram into circuit diagram. Again, here there are 3 or 4 stages. You have preliminary circuit diagram, you have preliminary level of bill of material with costing. Now, why this is important? That at the end of the design phase, you have made a product and the customer says, no, this is not fitting my cost budget. Customer will always say that they want a Akur Singhi Bahududi guy. But in practice, one has to convince the customer that for these specifications and for these particular features, whatever I have designed and the preliminary bill of material and the costing I have done is justifiable, and I'm sure then the customer will accept that. So after the preliminary level, you go to the next level, intermediate circuit diagram. Again, do the exercise once again for the bill of material and costing. And when you have reached the level, start ordering the special components. You'll find that not everything is available at short notice or extra. Some of the components, you may have special connectors, you may have special component in that may have typically 4 to 6 weeks delivery time. So start ordering the special components. What are the routine components which are already there in store? Don't bother about that. Some products may require some initial breadboard testing, because to prove your concept, you have to wire up on a what is called as a zero board, and make sure that that circuit function is tested satisfactorily to a sufficient depth, so that you can then go to the next level. Sometimes you may have initial breadboarding, final breadboarding, and based on that you draw the final circuit diagram, which is ready to make the PCB. For PCB design, if you are using a good software like Altium, which has got a lot of features and facilities, it helps you to generate automatic bill of material at the end of your design process. And that's where you come to the final bill of material costing. By the time you have done the PCB, where you have decided everything, where the connections will be, where the power supply connector will be, where the display will be connected, what are the input outputs, then you finalize your mechanical design also. These has to go hand in hand. Otherwise, later on you find that you have designed an excellent PCB, but then the mechanical engineer says, no, these clearances and this one, I can't fit it into the readily available housing. And every time making a custom housing adds to cost. So one has to be judicious about these aspects. Now, this is a typical diagram. The quality is not very good, but I apologize for that. You'll find that there are two ways to draw the circuit diagram. One is at the block level, where you don't worry about the IC pin numbers, but you draw a block which shows the inputs on the left-hand side, outputs on the right-hand side, the positive supply rail on the top side, and the signal grounds. There may be multiple grounds, isolated grounds on the bottom side. One thing I would strongly recommend, that those who have heard about the European magazine, Elector, that gives an extremely good presentation of how to draw the circuit diagrams. And if you follow such systematic method and not haphazard, like you put analog section on one sheet, the digital section on another sheet, the interface ICs on another sheet, that is okay for the PCB designer who can connect those signal names in his brain and actually when he is doing design. But a third party who is looking at the circuit diagram, he doesn't get a consolidated idea. So something which is to be connected directly to the microcontroller, you should show it close to the microcontroller. Say, for example, crystal as an external crystal oscillator for your microcontroller. Show it next to the microcontroller pins, appropriate pins, or reset circuit, or the decoupling capacitors. If you show it separately, then the PCB designer may tend to put these decoupling capacitors between supply line and ground line far away from the chip, and defeating the very purpose what the manufacturer says, that the decoupling should be as close to the IC pin as possible. So this is just one example where it takes the pinouts of the actual IC into consideration. Most of the ICs are now quad. All the four sides have the pins, and one has to decide in what way the circuit diagram will be drawn. A good circuit diagram is also a good starting point for making a good PCB. So be careful about making your circuit diagram itself. Now, this is circuit diagram from Elector. You find that the 40-pin chip, and there are a lot of wires crisscrossing for MAX232 for the RS232 port connection, the LCD display. But there are better ways to draw the circuit diagrams. In this case, this is a typical Elector diagram. You see the difference between the previous one and this one. And this looks so systematically. It shows the power source, it shows the LCD connection, it shows the switches as an input going to the thing. So this is one of the good example of making a circuit diagram. Now, in case if your circuit diagram has got too many parallel connections, then you can show that in the bus form. Like suppose you have signals A0 to A7 address lines, or A7 to A50. So that can be shown as a bus, because when these signals are going to the other component, they would follow the same order, LSB to MSB, and one can draw a very neat and good circuit diagrams which are helpful not only for the designer, but for the production people, for the debugging people, for the testing engineers, for the service engineers. So it makes life of everyone comfortable. So we have seen that PCB layout, PCB artwork, this is also an art. In the layout thing, which are the circuit sections which draws heavy current, that should be close to the connectors where the power enters. You should not have too many PTH because the plated through holes have very thin layer of copper conductive layer, and in a hostile environment, the first thing to fail on the PCB is the plated through hole. You must have got that experience. Some people just put the cut leads of the resistor and solder from the both sides to make the PTH stronger. The PTH should be for signal transfers and not for current transfers. Otherwise, excess current drawn by any section can cause the plated through hole to blow. Some people, PCB manufacturers and the PCB designer have different terminology for these plated through holes. They call it a via. Most of the embedded designs you can do with 2-layer PCBs. Some special cases you may go for 4-layer, 6-layer, 8 layers. But the blind vias, or whether the vias need to be covered with solder mask, you need to discuss with your PCB supplier and make sure that what you intend and what the PCB manufacturer gives you matches with each other. High frequency sections or analog sections, you should not put the components arbitrarily at random, but group them function wise and put them as far as possible. If you have an input connector, put the circuits related to inputs close to that connector. If you have an output connector, put the relay drivers or the transistors or anything, typically ULN 2803 is used for relay driving. So place it. So the first part is layout is as much important as doing the actual artwork. Now, one interesting observation I would like to make, LCD 16 pin connector, it has got a particular order of D0 to D7. Nowadays with microprocessor, you at least had the 8-bit ports where the bit order was from LSB to MSB on the consecutive pins. But with microcontrollers with multifunction pins, you find that this particular old order of LSB to MSB is not maintained. So if you are connecting LCD and just to match with the LSB to MSB, if you have to put too many PTH, best is to avoid that, make a direct connection and provide a lookup table in your flash memory where these bit swapping, like suppose your microcontroller LSB is connected to the MSB of LCD, but it won't work. So you do the bit swapping in a 256 byte, that is 256 byte 8-bit table in the flash, so that when you output from the microcontroller, the LCD still gets the information in the correct order. In ARM microcontrollers, you have what is called as bit banging, bit banding. So each individual bit can be treated in your software and turned on or off, or you can group bits together. So a lot of new facilities are there in the ARM Cortex microcontrollers, and the PCB designer needs to be aware. So in a circuit diagram, suppose you are allocated UART channels to particular 2 pins, like Silicon Lab, the crossbar matrix does it on its own. So one has to be sure, but with microcontroller and multifunction pins, at the time of PCB design artwork, if you find that you can swap the pin functions and you can change the allocated pins, the ST microcontroller or similar software microcontroller companies provide you the tools to do the reallocation, and that you can carry forward in your PCB artwork design. So initially, don't order 100 PCBs, 50 PCBs, order 5 or 10 PCBs for your prototype development testing. Once your prototype PCBs are there, and if the special components were already ordered at the time of your bill of material finalization, then by the time your prototype bare PCB comes, you would have the necessary components arrived at your desk, assemble and test the prototype. In terms of software design document, there are 2 approaches. One is bottom up and the other is top down. In case of bottom up, you develop individual modules and then integrate together. Whereas in top down design, you start designing from the top, in the sense, like suppose you are going to get some analog signal input. So at the top level, you just put a block and name it as the analog inputs. Now, how to get that analog input signal into your microcontroller memory is the detailing part. So the software design documents, many people, they say, oh, it is there in my head. I don't want to put it on paper for the fear of, anybody else reading that. But that's not a good practice. Whatever the software you do, you have to generate a design document for that. A good practice calls for the flowcharts and state transition diagram. In the next slide, I'm going to show you that. You may revise that first level flowchart, which is at the overall level, to a more detailed level in the second level. You may do at the final level so that you spend less time in coding. Many people call themselves as programmer, but they want somebody else to give them the flowcharts, and they would only translate the flowchart into the code. But best is to draw yourself the flowcharts, because that gives you the clarity of what you want to do, what the microcontroller ought to do. Remember that microcontroller is a sequential machine, and the field programmable gate arrays are the parallel kind of machines. So one has to know the plus points and the minus points of microcontroller in a sequential operation, and organize his flowchart accordingly. You'll see some examples. Software coding, you can do standard modules. Like suppose I have a UART function, so I have a standard module. I have a 16-character 2-line LC display, so I have a standard module for that. So such modules can be there. Some modules can be custom. You want to calculate root mean square value of your analog signal. So you may not get ready-made software for that. So you will have to write a custom module for that. So software coding, integration of all modules, where for each module you have defined the input and output condition. You pass on parameters when you call a particular module, and the module generates the necessary parameters and puts it into the memory, where memory is a common link between your different programs. And initially, you may not have full-fledged setup ready, so you will do some software modules testing by simulation. So this is just one example. There can be better than this also, but it is important. And in Google, you'll find flowchart tools, flowchart symbols. Each there is an action and there is a decision. Now, decision has got only two branches. Either the decision passes, which you say yes, or the decision test fails, no, and then you decide where to go next. And the entire microcontroller operation is like a continuous loop. It's not that you have a start and end, but at the end you go back to beginning and execute. Like PLCs, the famous flowchart is read inputs, store it into memory for the time that you are going to do calculation, calculate, generate output, update physical outputs, and go back and again read inputs. That's how the PLC keeps on working. And then you may have fixed loop time, you may have variable loop time. So your software has to know this, whether you have fixed loop time or variable loop time. And if certain parameters are going to be like, say, ramp rate, the soft start for the motors, soft step down. So you can decide whether you want to do under timer interrupt, ramp up, ramp down, or you want to use the loop time information. So flowcharts is, I would say, is a compulsory part for the software designer. There may be complex flowcharts which shows more than the storage options or the communication option, data logging option. So these are just some examples of the flowcharts. Now in Pune, you have automotive sector, and this is a perfectly fitting example. Like either the car is stopped or car is running at the constant speed, and when the state transition takes place, if you are accelerating or you are de-accelerating when you are applying brake. So this is a very simple state transition diagram. You can find more complex state transition diagrams for old fax machines, for telephone sets, whatever you do, there has to be such state transition diagram drawn by the designer, software designer, confirmed by the hardware designer, that yes, that is the way to go ahead before the actual coding starts. So here parallelly, you have to know what are the kind of test jig requirements for that, how you are going to test the hardware, how you are going to test the hardware and software together, how you are going to do mechanical assembly. And as they say that the test of the pudding is in eating it. So the real test of your product is when you do monitored field testing. You cannot be there at the field site for all the time. So sometimes you have to leave it to the customer and do some unmonitored field testing. And when you get field feedback, you revise your designs. And whenever the product is to be subjected to the independent testing labs, you have to do that, get the type test performed. You have to write the user manual for your product. You have to have a separate servicing or maintenance manual for your maintenance team. And equally important is design the literature for your sales and marketing department. So in this manufacturing process planning documentation, everywhere I have given the stress for documentation, because that is the best way of communicating information between different groups, and all the concerned parties should be informed. Even after the product is released to the market, after 6 months, after 1 year, you may find that customer needs some different feature or facility, and that has to be communicated to the production team by way of engineering change notes. Sometimes the silicon chip manufacturer provides you errata for their chip, because the chip design is also equally getting complex. And when the silicon manufacturer provides you some workaround solutions for that. One
Your
of
time
the
is up. Time is up.
just another 2 minutes. The topic which gets neglected during design is the failure mode effect analysis. So I have shown some examples here how to do risk priority numbering and their ranking. So one can prepare the Excel tables in that and fill up the information. This requires contribution from each and every person connected with the product development or project. And this is where you find that my stress is more on the making sure that you do everything systematically and document it, so that it is important to communicate. So you have these various standards which you can follow right at the design stage. This is a better clear screen. Various standards, what are applicable to your product design, one must you have IP standards. Some people are not aware of the existence of such standards for ingress protection. So this is the list here. You keep on updating yourself. You have product safety standards. Under product safety testing, various tests are performed by international laboratories like Intertek or UL, or many other similar laboratories are there. So you'll find that one has to be aware of this. Your product is not going to be always used in an air-conditioned environment. So you need environmental test, you need shock vibration test. You have to select between whether you want to use a fusible resistor or the actual fuse. There are advantages and disadvantages of each method. You have to know why the green masking soldering is cheaper than the other types of masking, whether you want to brown or blue color. This thing explains what is the logic behind green as a common thing. Many people you find complain that my microcontroller gets hang, and that is the EMI EMC not taken into account. So there are certain tips here. Pre-qualification tests are important. Electrostatic discharge is a known phenomena, particularly for CMOS ICs. So one has to be careful. 16-character display, people use the English language, but very few people are aware that you have alternate language sets like Russian or Japanese. And talk to your LCD supplier and find out which version you can order for the other languages. There are low dropout regulators everybody is using. Few people are aware as to how to make that low noise, low dropout regulator with less noise, because same 3.3 volt is used for digital circuits as well as for analog circuits, analog reference. So one has to know such finer details. Ceramic capacitors are based on their dielectric and they have different properties. For crystal oscillators, if you are using ceramic capacitors, they have to be temperature compensated version called as NPO or CGO, so that the oscillator frequency remains stable throughout the working range. Many people use SMPS in their product design, and some people are not aware as to how to add the substrate. The simple solution is across the anode cathode of TL431. If you put a 10 microfarad capacitor, your SMPS gets a property of substrate. So this shows a typical example. One has to be careful when you are using such kind of work pins and sockets, that the sockets need to be of phosphor bronze for a better grip and lower contact resistance. Low cost male-female connectors are typically in brass, but if you insist on the supplier, manufacturer, talk to Protectron, then make sure that you have the phosphor bronze as a contact material for high reliability and long life. So I'm really thankful to all of you for giving me this opportunity, to the organizers, my friend Mr. Vilas Rabde, and his team members, Dr. Uttam Avari sir, engineer Mr. Vasanta Pandharkar, and of course you all knowledgeable audience. So there's a disclaimer that whatever the photos or the images used are the property of their respective owners, and I don't claim anything against their trademarks and registration. So thank you for listening to me for the last 50 minutes or so. Thank you so much.
Thank you, Jayakrishnan Puranik, for this wonderful overview. We really appreciate your efforts, deep study and knowledge, and you really taken the subject to the hearts of the most of the design engineers. And we have few in the group. So without spending much time, we will give some time for question and answers. We have very little time now, friends, just 10 minutes. But shoot out your questions and let's see, plus identify yourself and then ask the question.
If there are no questions, then I will assume that everything you have understood very well.
Sir, I will start.
Yeah.
I'm Makarand Vaidya.
Yes, Mr. Vaidya. Please continue.
I will start with one basic and very obvious question. Please put a light on PLC versus embedded in the acceptance, in the context of reliability, and in general easiness of a system designer, so that he can take a decision.
Yeah, it's a very good question, and I'm happy to answer because I had the experience on both using PLCs in various projects from Nelco for steel rolling mill applications, and of course other organizations for the embedded hardware. Now, as the PLC manufacturers are taking advantage of the developments happening in microcontrollers and the hardware design, they make the PLC hardware mass manufacturable and obviously far more reliable than what you can think of in the embedded system design in terms of galvanic isolation, in terms of product environmental testing and many things. Plus the PLCs also have a firmware internal, because if you are doing programming in relay ladder diagram, ultimately that relay ladder diagram gets converted into the executable code on your PLC microcontroller. So this conversion is done obviously by the PC-based software. So in terms of hardware reliability, PLC is superior. But in terms of cost, each and every application may not be possible with PLC. Though now Omron has come out with PLCs costing as low as say 16 input, 16 output within 10 to 15,000. But if you are designing a custom hardware embedded system, you may do it in 5,000. If the hardware is designed carefully, embedded hardware, then it would perform in terms of execution time better, because in PLCs you have other software overloads. There is housekeeping. So if your 20 milliseconds goes for your actual computation, there may be 5 milliseconds for the housekeeping. So PLC is good where you want to concentrate more on the problem solving, and the embedded hardware is good when you want to reduce the cost and have it absolutely custom configured or custom made for your applications specific. So it's a designer's decision whether he wants to use PLC and solve the problem. Like suppose you want to do a 3-axis stepper motor controller. I know people are doing 3-axis stepper motor controller using PLCs. They have designed the embedded hardware also. So it is really a tough choice. But once you put onto paper and work out the costing, you will be able to take a decision whether you want to go ahead by designing a custom or a standard microcontroller which you can customize by programming, or you want to use the PLC. I hope I answered your question fully.
Yeah, please go ahead. Other question?
Yeah. I find Mr. Ugle, my good old friend in the group.
Yeah, Prank sir, good morning and all the team member. Prank sir, I request you to give some highlights on the artificial intelligence, means AI technology, which is a buzzword. So AI application related, which microcontroller is suitable, and how we select this microcontroller based on the peripherals.
It's an interesting question. Thank you, Mr. Ugle, for asking this and reminding me. Our organization, which does the licensing for the silicon manufacturer, have come out with a large variety of microcontrollers with embedded kind of facility for artificial intelligence. You have the hardware core to do some neural network processing. Unfortunately, I didn't get any opportunity or experience to work on this except keeping myself up to date by studying what is available in the market. But the future trend is definitely that you have very many embedded things into the core, your silicon chip configured around your basic ARM Cortex microcontroller. So one really needs to learn this from the beginning. The implementation of artificial intelligence or machine learning, and gradually the more and more products would become far more superior and intelligent by selecting the processors which provides you that capability. Intel and ARM Bangalore organizes training programs of typically 1 week to 2 weeks. So whenever I get a next opportunity to myself attend such a training program by ARM for using this artificial intelligence facility in the designs where you make your product more powerful than what it is today. So yeah, I'm a student in this field, and I want to learn the new processors which provides the AI facility inbuilt and how to explore that. It's a new topic. I'm eager to learn, but at the moment, I'm not able to say much beyond what I have. I keep on reading from the different manufacturers and suppliers. So thank you, Mr. Ugle, for asking an interesting question.
Okay, I think we have few minutes left. Last question we will take.
Yeah. There's a question related to field program gate arrays and JTAG. Nowadays, all the microcontrollers come with this JTAG specification, Joint Test Action Group, because as the processor becomes more and more complex, you can't have enough pins on the device vested for as a test input pins. And therefore, the JTAG provides a peripheral interface to all the internal logic. You can do single stepping, you can watch program counter, you can watch flags, you can watch registers. So there is no point in using a processor which doesn't have JTAG facility. Otherwise, you'll be spending inordinate time in debugging your software and hardware products. So JTAG is very important. Field programmable gate arrays allow you to do many things in a parallel manner with your microcontroller. And you have the configuration tools for field programmable gate arrays, which includes the microcontroller core as well as analog function blocks. So whenever you are thinking of some very high speed operations, like say active harmonic filtering, something similar to that, or any defense projects where you want to run DSP algorithms in a parallel manner, then obviously FPGA is the thing to go. But I myself didn't get any chance to use FPGA so far. I'm keen to use FPGA, learn FPGA, and practically implement it. There's a question about the failure mode effect analysis. Information is available on Google, but what I have put it in the slides is from my experience that it is not necessary that you wait for the product to go into the field and then wait for the failures to come and then analyze it. It is right at the design stage. One has to get involvement of various people and find out what can go wrong. The designers does everything with good intentions, but sometimes he may miss something. Like suppose you have relay output and you have a common fuse for that. So what happens for the if the fuse blows? Because sometimes the field wiring person may not connect the contactor coil neutral earth correctly, and whenever the relay switches on, it directly short circuit phase neutral. So your protection fuse will blow, and in that case, the circuit would be declared as unhealthy. So try to look at your design in every possible aspect. What are the chances? Suppose your product is designed for 0 to 320 volts, and suddenly instead of phase neutral voltage, there is a phase-to-phase voltage appearing on that. And obviously your circuit is not designed to handle phase-to-phase voltage. So what kind of clamping you are providing? What kind of failure that can happen? One has to think. This is more or less a brainstorming exercise. And I would say that before the product is released to the market, this failure mode effect analysis and critical failure analysis should be carried out by the entire team. which should involve the sales marketing people, the service people, maintenance people, the designers, production people, and try to do justice. The idea behind that is to come to a conclusion that your RPN number is 1. If everything is taken care of and responsibilities are fixed, that is, if some problem occurs at manufacturing stage or at field stage, then who is responsible for that? I'm not saying that one can design a product which is totally foolproof. I mean, some people ask that your product should be designed idiot-proof. So you have changed some parameters and you have not pressed the save key. So obviously the parameters are not saved in the memory. So do you organize your software to warn the user that having entered in the edit mode, do you want to discard the edited information or you want to save it for future reference? So the intelligent programming really calls for this kind of experienced actions on the part of the hardware designer and the software designer. And I think you will do Google search to find out more such methods, but everywhere this scale is on the 1 to 10, where 1 is the less severe, 10 is the severe thing, and you arrive at the conclusion based on your failure analysis.
I think that's the last question we handled. Thank you very much, Jai Krishna Paramik, for this wonderful presentation today. We really appreciate. This presentation will be available on YouTube very shortly, and you can watch it at your leisure time. I will announce for the next Sunday. It's a special tech talk we have organized by Mr. Mamtani, Saksham Mamtani, who is a student, just completed his graduation and will be going to US for his further graduation. He will be talking about materials for battery. You all know Tech Forum, we have focused on electric vehicles and various parameters, rather various parts of the electric vehicle, and battery plays a very vital role in any EV, rather growth of EV technology. So a lot of R&D organizations are busy in developing new batteries and material required for that. Saksham has done his internship in Mercedes, and he'll be going to Pittsburgh for his further graduation. We always believe the youngsters possess a lot of latest knowledge, and they are the driving force for new technologies. So definitely you all are requested to join us next Sunday morning at 10 o'clock for a special tech talk on materials for battery. If Saksham is around,